In this video, I'll be showing you how we computed the CAN bus timings for both on the Jetson and on the STM32 microcontroller. So if you remember, we are using this PCB here, which communicates through two CAN buses. And the CAN bus is a very strict protocol in terms of delays and timings, in the sense that each node in the network, be it on the Jetson or this PCB, need to have the exact same timing configuration in order to work. And even having the same configuration does not guarantee that the communication will be successful. And we need to configure it in such a way that the expected speed and the expected load on the bus will be within the limits and within the configuration parameters that we set. So in this tutorial, I will show you how we choose the different parameters and how we compute the timings for the bus. So in the Xplore Notion technical notes, I think it's somewhere on the Slack, it's in the documentation for the electrical side. I written a small calculation which is a bit outdated, so I will show you how to compute this. So how do we compute the FD CAN bus timings? There is a nice document here which defines all of the bus timings and how to compute everything. So I will go through it very quickly. So first we need to define our bus length for the wires. So in our case, I will set the maximum bus length to around 5 meters, which is quite a lot because the rover is only like 2 meters or it's 1.3 meters in length. But with the number of cables and the fact that we have to go up the belt and down in the drill makes the bus a bit longer, but not that long. So I just set it at 5 meter. And the delay of the signal in the cable is around 5 nanoseconds per meter. Then if you open the PCB here and you look at the transceiver of our CAN bus, so this is on the main PCB here, and this is in the node-to-node connectors, you will see in the datasheet the different timing specifications for our chip. So here you will see the propagation delay time, and these can be used here to compute our total propagation time. So the delay time will be given by first the delay given by the length of the bus and the propagation length, and propagation speed, I mean. So for 5 meter and 5 nanosecond per meter, that gives us 25 nanosecond. And then we have the TX and the RX. So it's 75 and 65. So these are given, I think they are given somewhere here and here. So it's for the TXD and for the recessive to high input. So you have 75 and 65. And the computation is done by multiplying the sum of the 3 times 2, which gives us 330 nanosecond. Okay, so this is for the propagation time. Another parameter that we have to look for is the oscillator tolerance. So if you look at our chip here, if you go inside of the microcontroller section, you will see the crystal that we are using for this particular PCB. So if we have a look on DigiKey or whatever of the crystal, we'll have here the stability, and we see that we are at 15 parts per million, which is pretty good. Okay, so this is our second parameter in the calculation. And then what we can do is, what we have to know, I mean, is the clock frequency. So this is not very important, but it's just something nice to know. So if you go inside of the STM32Cube IOC file, you will see in the clock configuration how I have decided to configure the FD CAN bus. Okay, so let's have a look at the timings for the ORM firmware. So I just went inside of the IOC, and in the clock configuration here, you can have a look at the FDCAN, and we are working actually at 80 megahertz. So this is what we've decided to configure it to. And once you have all of these, you can start calculating the FD CAN bus timing. So for this, we use the CAN FD bit timing calculator. So first, we'll need to input our clock frequency. So in our case, it's 80 megahertz, which is 80,000 kilohertz. The clock tolerance is 15, and we have a node delay that we've just calculated of 330 nanoseconds. Okay, we just delete this device and we add our CAN device. For the bit rate, so the CAN bus, the standard CAN only has the nominal bit rate, which is the bit rate at which it will send everything, like the header as well as the data. In the case of CAN FD, which is flexible data rate, we will have two different bit rates. So the first bit rate is just the nominal bit rate, which includes the things that come before we send the data. So if you look at a CAN FD message, you will see that there is a lot of checks and other types of data that is sent before we actually send the data. So the arbitration phase here, and this is sent at a certain frequency, while the data is sent at another frequency, so to speed up the process. Okay, so what we do is that we will send it at different frequencies. So if I look here, the settings that we used for our project is 500,000 bits per second for the nominal bit rate, and we choose to use 2 megabits per second. Okay, so I just recalculate. And now here are the most important settings that we have to choose from. So we need to choose the sample point as well as the prescaler for both the nominal and the data bitrate. In our case, we've decided to use a very standard sample point, which is used in CAN open and other types of protocols for the nominal bitrate. So this sample point is 87.5. Okay, 87.5, which gives us some settings here. And for the data bitrate here at 2 megabits per second, we chose to use a sample point of 90. So this is really trial and error. And if you use a bad sample point, you will have a lot of errors in the bus. And you will see that you will not attain the performance that you want. So the higher the data bitrate, the more this sample point will become critical, and the more prone to errors, and the more the clock tolerance and other stuff will come into play. Okay, so now we also choose a prescaler of 2 for the data, and that will give us all of the settings that we need to include in both the Jetson, but as well as in the microcontroller. So now let's go into the microcontroller side. So in the microcontroller side, if I go in the IOC file here, I will have access to the FDCAN configuration. So if I look at the FDCAN 1, the FDCAN 2 is configured in the exact same way. Here you will see that I can change some settings. So now let's go into the nominal part. So we have a segment 2 of 20 as well as a sync jump width of 20. So let's look for this. SGW is sync jump width of 20. All right, so this is correct. And we have here a nominal time segment of 20. This is the nominal time segment of 20. And we have a prescaler of 1 for the nominal prescaler as written here. For the data at 2000 megabits per second, we have here a time segment of 17. So here it's a time segment of 17. We have the time segment 2 is equal to 2. So time segment 2 is defined somewhere here, data time segment 2 of 2. And we have the sync jump width of 2 for the data segment. Okay, data sync jump width equal to 2. And we also set the prescaler is equal to 2. All right, so you can see here that the computed nominal speed is correct. So it's equal to 500,000, which is exactly what we put here. So what we put here. So it's the timings are correct. So some of the other settings you don't really need to know really, but here you can see that we've also set some filters and the number of filters. So I invite you to have a look at this. But basically, what this means is that the more the number of filters we have, the more we can filter the type of message that we get. So the ID of the message, we can filter out what message this microcontroller should receive. 64 is overkill, and we only use actually 2 out of 64 filters. So this is not necessary, but I was a bit lazy to change this. And yeah, so these are also some other settings. So we just set it as the maximum number so that we could get as much data as possible. All right. So this was on the microcontroller side. And now how do we actually do that on the Jetson side? Oh, and also you have to change it to FD mode with bitrate switching here. Don't forget this. Okay. So now how do you do this on the Jetson side? So on the Jetson, we can have a look here at this video that I recorded. Okay. So first, how do we configure this? So we've actually created an executable file, which is started at every startup of the Jetson and configures the CAN bus. So it is located here at the root of the Jetson. So you just need to go back 2 folders, and then you go in the user, then you go in the local folder, and in the local folder, there will be this canfd.sh file. Okay. So in the canfd.sh file, if you open it, so I just use code to open it, and you will see here the different settings that we are using. So first, you will need to configure the BusyBox. So this is a library that is necessary for the CAN to work. Afterwards, you will need to enable the mode probe for the CAN bus. Then you will have to bring down the CAN interface. So this is because we need to bring it down before configuring it. And here are the settings that we set inside of that we computed before. So we have 500,000 for the nominal bitrate, 2 million or 2 megabits for the data bitrate. We have a sample point of 87.5 for the data, for the nominal, and 0.9 for the data. Another setting that is very important and something that I don't really like, but it was the only way to have it work, is the one-shot setting. So the one-shot setting basically is a setting that is used in order to not have an acknowledge, because usually the CAN bus, when it sends a message, it also checks for an acknowledge from whether node is receiving the message. And we observed that if we set it with an acknowledge, and if the node was not connected, then it would go, it would just start piling up errors. And in the CAN bus, when we exceed a certain amount of errors, the bus goes inside of an error state, which we can hardly recover from. So usually we can recover from this state with the restart millisecond option here, but it was not working very well. So this is why we chose to use this one-shot option here. You can also observe that I am using the FD on option so that we can use it with CanFD. Then there is the TXQ length. So this is basically the number of messages that we should keep in the buffer in case we miss some messages. And then we just set here the interface for the CAN bus. So MTU72 is just to enable also the FD CAN interface. So this is it for the Jetson part. For just, this is like the software enabling configuration that we need for the CAN bus on the Jetson, but there is also the hardware part that we need to configure on the Jetson. So I will have another video here that I can show you. I'm not sure if this is this video. Yes, this is it. So now we need to configure the actual hardware CAN bus on the Jetson. Normally, if you haven't touched anything, it should already be configured on the Jetson, but I will still show you how to do this just in case you have to do it. So first you need to go in the opt/NVIDIA and I mean, don't need to go inside. You just need to execute a program from this. So if you execute this program, which is jetsonio.py, just type in the password of Xplore, a small window will appear here, and you can configure the Jetson 40-pin header. And if you just extend this window, you will see here the configuration. So you can see here that the CAN bus is configured. We have the CAN 0 and CAN 1. And it should be that way in order for the CAN bus to work on the Jetson. If it is not working this way, then you need to configure it manually. And if you have issues doing this, then please contact me because I've had this issue before. So you can also execute this command here, configure by pin, and if there are no errors in the configuration, it should execute with no issue. So here we can see all of the different pins and what functions they have been associated with. All right, so this is it for the configuration of the CAN bit timings on the Jetson, on the choices that we made for the bit timings, how we computed it, and how we configured it on both the STM32 and the Jetson.